So last time I think I finished up talking about sunlight. Any questions that you have on sunlight and the various things that happen to it as it comes through the air and the rest of the world? Just to put it in perspective of the next topic, which is discharge lamps, sunlight is light produced by it's blackbody radiation. It's thermal radiation from essentially a black surface, and that being the surface of the sun. It's kind of the simplest type of light. I should say light is light. It's still electromagnetic waves and all, but you can make it in more and more sophisticated ways. So the sort of the least sophisticated way of creating light is by just having a hot surface. And the hot surface radiates away lots of independent light waves. You have no control over the spectrum that comes out apart from the temperature of the surface. If you color the surface other than black, then you have some control. But for a black surface, it's going to radiate a spectrum that has to do with the statistics of thermal energy and how it's distributed. And it follows certain rules. And the hotter the surface is, the higher in frequency the spectrum peaks. And it moves according to what is the Rayleigh-Jeans law. There's a name for the whole law of that radiation. We're going to start making it with more and more sophisticated techniques. And the first being discharge lamps. And that would have been the end of the story almost 30 years ago, because light-emitting diodes, which is what we'll get to next, and lasers were babies at that time. At this point, they're so ubiquitous that they're going to become the dominant source of light in your world other than the sun itself. Anyway, just to start with then, so what are discharge lamps? I should just identify them. These lights overhead, so-called fluorescent lights, are a form of discharge lamp. Other ones you've seen are the advertising signs, including neon signs. And I'll pin down a little bit what neon sign is. It's used more broadly than literally a neon sign. And then other discharge lamps are mercury vapor and sodium vapor lamps that you see in like warehouse stores and street lights, but even there, that's evolving. So that's a couple years from now, I'll have to change the topics. Okay, so the first question here, just to get us started, is a fluorescent lamp tube is coated with white powder on its inside surface. If you've ever broken one, you've seen this white powder comes out. Is that powder, if it weren't there, if you just eliminated that powder, what would the lamp look like? And I got three choices: brighter, dimmer, about the same brightness, but with a really bright line in the middle of the glass. You okay with the question? How many think that it would be brighter? How many think it would be dimmer? How many think that it would be about the same brightness, but with a really bright light in the middle? Okay, it's a pretty even split, primarily for the last two. I mean, nobody's really voting for brighter. We'll come back to this shortly, so I'm not gonna spill the beans yet. Okay, so some observations about discharge lamps is they often take a moment to turn on. That was certainly true of fluorescent lamps 10, 15 years ago. Now they're so fast you can barely tell there's a turn-on time. But some of them you probably watched those. Like a gymnasium, if there's a power failure, the lights turn off, there's a problem getting them to come back on, and it takes a while. They come in a variety of colors, including white. So neon sign, of course, isn't. They're often whiter than incandescent bulbs, meaning that they have more blue in them. They're more able to make blue than the hot filament in a tungsten bulb, for reasons that we've already seen. You can't get the tungsten bulb filament hot enough to produce a lot of blue, so you do better with other techniques. They sometimes hum loudly. So this one, for example, this is a little neon lamp. Can you hear it hum? It's driven me crazy for years. But that hum it's so-called 60 cycle. It's associated with our power lines. That 60 cycle per second power lines. It shows up in the lamps by accident, and particularly when the lamps get old and parts in them start to fail, they start to hum like that. So it's an obnoxious sound of a 60 cycle world. And the lamps often flicker before they fail altogether. They develop, the way in which they go bad is sort of complicated, more complicated than an incandescent light bulb. When it goes bad, the filament's gone. There's just nothing. With a discharge lamp, sometimes there's something's left, but it's not usable. Okay, so questions we'll go after, the first of which is why? Why even have the incandescent light bulbs? And that's a reference back to the era of the why even have fluorescence in other discharge lamps? That goes back to the era of the incandescent light bulbs. Why are we getting rid of those? And the answer is that they're inefficient energy-wise, incandescents. If you put 100 watts into an incandescent light bulb, you get something like 5 or 10 watts of usable light. The rest is lost as just sheer heat flowing out of this hot object, as hot air, for example, and as infrared light, which is a part of the heat transfer, but it's a part of the heat transfer. It does involve electromagnetic waves, but ones we can't see. So what's the point? And incandescent light bulbs put most of their thermal radiation in the infrared part of the spectrum, which is useless to us except as heating. So incandescent light bulbs are fine if you want to keep the French fries warm, but they're not so good for illuminating your house so you can see what's going on. What else about them? Yeah, it's less than 10% of the thermal power is visible light. So you can do better. How do you do better? Don't use thermal light. Don't create the light the really old-fashioned way, which is to get something hot. Create the light using more sophisticated physical processes, and that's what discharge lamps do. Okay? Second question is, how can colored lights mix so that we see white? And this is leading into the idea of a fluorescent light. Those lights up there are producing a white. You can buy fluorescent lights with different types of white. I told you about that the other day. You can buy different color temperatures. So they subtly change the spectrums that they produce. They're not making a thermal spectrum exactly. Or not making it by way of heat. They're trying to assemble it. And not only can you get different whites, a warm white, a cool white. Those are bad. I don't even want to use those names. You can get color temperatures near the sun and color temperatures near the tungsten, lower temperature, incandescent color temperatures. You can also get truly colored fluorescent lamps, and those are used routinely in signage. When you drive by someplace and it's got bent glass tubes that are glowing pretty much anything but red, any color but this. This is a true neon cyan red. All the other colors, they're just fancy fluorescents with colors. So my purpose in this question is to say, okay, so if they're creating a spectrum to make you see white, what exactly are they doing? And what does it mean to see white or other colors? And so this is a little bit of a story about human physiology. So you ought to understand how color vision works. We don't have in our eyes some sort of spectrum analyzer that looks at the frequencies of the light and says there's some light at this exact frequency and some light at that. No. It's way more simple than that. We have in our eyes sort of 4 types of light sensors. The first, which has nothing to do with color vision, is what are called rod cells. They are very light-sensitive cells. They're present in our retina, primarily in the peripheral vision, although there's some in the central vision, which is called the fovea or the macula. There are some rods there, but by and large, it's in our periphery. And the rod cells have no color sense. They see black and white, basically, and they give us our night vision. So when you're walking in very dim light, you don't see much color. What you do is you see essentially black or white, whether you're aware of it or not. And that's the rods picking up just the hints of light. Okay? And you can see you're most sensitive to this very dim light outside your focus, outside that central vision. So this is why if you really want to see something that's very dim, you look with your peripheral vision a little bit. And it's just human nature. You don't look right at it, look a little off it, there you see it. dim glow, okay? Moreover, it sees the broadest swath of colors, of frequencies. You can see deeper into the infrared with your night vision, basically, than you can with your color vision. So that's a little bit about the rods, okay? The other kind of light-sensitive cell we have in our retina, they're the cone cells, and they come in 3 types. There is a type that sees primarily the lowest frequencies of the visible light, the red sensors. So we've got red sensing cone cells, and this is me trying to reproduce from the literature measurements of the sensitivity of the 3 types of cone cells that we have in our retina. It's, so it's an approximation. But our red sensitive cone cells see primarily light. They're most sensitive to light at 600 nanometers, which is in the red, and they go out as far as about 700. Oh, come on. Oddly, they have a little bit of a sensitivity to the sort of the violet end of the light spectrum as well. So, if you expose these cone cells, the red cone cells, to light at 600 nanometers, they go, oh yeah, no, I see it, it's great. If you expose it to light at about 500 nanometers, they're just not sensitive. So that's the spectrum of sensitivity. I'll leave it at that. Okay, we also have green sensitive cone cells that see this light, they're sensitive to light sort of in this range in frequency, and we have blue sensitive cone cells that are sensitive to light in that range. And that's all we got. So how do we see all sorts of colors and the ones in between these? Well, if you take your eyes and you look at light that is as a pure frequency somewhere out here at the extreme end of the reds, that's the only cone cells in your eye that will respond and say they see anything are the red sensitive ones. And so they'll go, yeah, we see it. Your brain will interpret this as this is deep red light. It's not triggering the green or blue sensitive cone cells at all. But as you come in more towards 600 nanometers, the red sensitive cone cells are seeing this light, but so are the green sensitive ones. They're beginning to see it. And so your brain receives a message that we've got a bit of a mixture here between red and green. There's a little bit of both going on, and it'll start to see orange. So your brain interprets that as orange up here. And go a little further, say right here at this frequency where your red sensitive cone cells and your green sensitive cone cells simultaneously report pretty strong excitation, your brain interprets that as yellow. And so on. It goes across here, and you get into blues and stuff. And you get out here where both the blue sensitive and the red sensitive ones are going, yeah, we see light. Your brain interprets that as violet. Questions about this idea? With 3 different kinds of cells, you can see the whole rainbow spectrum just by the balance between how much those cells are excited by the light you're looking at. That means that if you go here, look at that orange or yellow. I'll concentrate on yellow. If somebody shines true yellow light at you, which is maybe about 580 nanometer wavelength. I'm using wavelength and frequency somewhat interchangeable. I hope you can follow that. Again, you multiply them together and you get the speed at which the light travels. So if you expose, you look at true 580 nanometer light, you'll see yellow, because your red sensitive cells and your green sensitive cells will both go, whoa, we see it, about equally. On the other hand, if you also look at a mixture of 2 different lights, one of them at 600 nanometers and one of them at 550 nanometers, the 600 nanometer light will get your red sensitive cells going, and the 550 nanometer light will get your green sensitive cells going. They'll be triggered about equally if you use the equal amounts of those 2 lights, and your brain will say, I see yellow. There's no real yellow light there at all. It's that your brain is being tricked. The right mixture of red and green makes you see yellow. Questions about that idea? It's pretty, it's pretty central to the whole way in which all computer displays work. Color printing, the whole works. So we can be tricked into seeing colors not by combining colors that trigger our red sensors, our green sensors, and our blue sensors, and you just use different mixtures of those three colors. So basically you work with a palette of three types of light. Essentially red light, green light, and blue light. And by juggling just how much of those three are present, you can make our eyes see all the colors. And incidentally, I should say that if our eyes see red, green, and blue in the right balance, we see white. Because that's how sunlight makes us see white, is it triggers all three sensors about equally. So you can mix these three colors, red, green, and blue, and make us see any color that we can see. Those, therefore, are known as the primary colors of light, as opposed to pigment. Pigment's a reverse process that I can talk about. But the three colors, primary colors of light, no one gets to choose these. Our eyes choose these for us. It's built into us. It is red light, green light, and blue light, because they trigger our sensors primarily, sort of dead center. You can play a little bit, but not a lot. And that means that if we take red light over here and green light over here, we put them in the same place in space and look at them, we see yellow. Because it triggers those pairs of sensors just the same way that yellow light would. Okay? The reality is that there is no true yellow light here on the screen. That computer display, this is, it's a projected display, but it's the same idea. If you come up here real close, you'll see that those actually are little teeny dots of red light and green light. They don't actually overlap in space. They're side by side just for technical reasons, but our eyes can't resolve them, and we see both. So they overlap on our retina, and we see yellow light. Right? So we're being fooled. This is magenta here. It's what happens when you expose our eyes simultaneously to red light and blue light. And over here, it doesn't look very good. Why does it look blue? Yeah, I mean, it is blue. It's just not very bright. This is cyan. It's not technically blue, but so these are basically caused by overlapping the colors. And then if you overlap all three, red, green, and blue, and there's white. And again, there's no real, it's not white light like sunlight. It's little dots of red light, green light, and blue light. Very close together, our eyes don't resolve them, and therefore they look to us like white. All right? I mean, next time you look at your phone or whatever you want to look at real close. You may need a magnifying glass, or if you put drops of water on the glass, you can see the little pixels. Yeah? Why do printers use cyan, magenta, and yellow? These three colors, magenta, cyan, and yellow. If you use them as pigments, if you use dyes that have those colors, actually, right? If you put yellow, for example, on a sheet of white paper, when it's exposed to sunlight, it reflects back all the colors, including red, blue, and yellow. Red, blue, and green. Okay? If you put yellow pigment on that paper, you ruin its ability to reflect blue. Because yellow has the two colors we see, but no blue in it. So yellow pigment, again, it should be called dye. Pigment also has the characteristic that it reflects light, it scatters light back out, which you don't have to do. Dye just is transparent, except for it eats colors. Yellow dye eats blue light. Okay? So wherever you put it on the sheet of paper, there's no blue coming back out. Cyan, here's cyan. Cyan eats red light. So wherever you put it, the paper no longer can reflect red. And magenta consumes green light. So wherever you put it, you can no longer see any green coming back. So by strategically putting cyan, magenta, and yellow onto the paper in patterns, you can sort of turn off its ability to reflect the mixtures of the colors in white. And you can, if you put yellow and magenta down simultaneously, it can't reflect blue or green light What does that leave? Red. So a mixture of yellow and magenta pigment on a sheet of paper will look red to you. Is that okay? So this is what, those are known then as the primary colors of pigment. And I'll stop suffering over pigment versus dye. The printers use the complementary colors, and there they are, the 3 complementary colors that come from overlapping 2 of them. Other questions? Yeah?
So I said one of your art classes as a kid, they teach you that the primary colors were yellow, blue, and red, and you combine yellow, blue, and red.
Yellow, blue, and red. Yeah. Yellow, and if this is sort of bluish, it gets sort of greenish. It's not a compromise. It's a not as good a set of primary colors of pigment. The real primary colors, magenta, cyan, and blue, cyan, yellow, sorry, think before I talk, are sort of too extravagant and expensive. So you make do with, well, yellow you've got, instead of cyan you go with blue, and instead of magenta you go with red, and it kind of works. It's not quite as good. These guys, these are better. Is that okay? Other questions? Oh, one thing I want to say about color vision. Some non-trivial fraction, particularly I think it's of men, have color vision problems. It's sex related. It's related to the Y chromosome. So they have difficulty. They have cone cells that don't distinguish red and green very well. They don't have the full. Their spectrum of sensitivity is not like this. It's a little. It's less complete, and therefore they can't distinguish these 2 colors very well, and everything. So this whole end of the spectrum gets a little bit muddied. All right. Other questions? Otherwise, okay, I'll go on. So the point of this is that if you're going to start sort of assembling light, particularly if you want to assemble white light, you need to understand how the eyes work, because you want to expose the scene to light that contains some red, some green, and some blue in essentially the proper balance. That will cause our eyes to see white and will potentially serve as a good source of white illumination. It's useful just in general for all the computer stuff you ever work with. This is what you're working with, and when you're playing with the colors on the palette of some paint program or whatever. In fact, you're dinking around with the balance between red, green, and blue light. Okay, so why does a neon lamp emit red light? And this is now a step in a different direction, because we see it as red because actually it's mostly a single color, really in the red. Okay, and the answer to this is this horrible statement that neon's quantum structure dictates light emission. I only say it's horrible because it brings up quantum physics. And so this is my excuse in this class to talk for a little while about quantum physics. I should say also that very few people currently study quantum physics. It's just a basic tool that all physicists use at this point. It's 100 years old, basically. And it is the way the world works. It's just a more accurate description of the physics of the real world. It has subtle effects. Most of its effects are subtle, I should say. But you can't ignore them if you actually want to get into the nitty-gritty of how things finally work. Quantum effects are most noticeable for little things, little objects, small masses. And that means things like atoms. You can't understand how atoms work properly without quantum physics. On the other hand, big things, yeah, they got quantum character, but often it's so hidden you can barely notice it. The quantum physics of the solar system is irrelevant. Too big, too much mass. Okay, so what's the story here? Well, electrons, which is part of the atoms, they obey the rules of quantum physics. And the electrons, rather than being little billiard ball particles, little specific objects. They spend most of their time moving in what are known as standing waves in an atom. So the electrons in an atom, rather than being little planets orbiting the nucleus, as is often drawn, they're actually standing waves about that nucleus. They're held in place by electrostatic forces. Electrons really are negatively charged. The nucleus is positively charged. Electrons build their standing waves around that nucleus, but they're standing waves nonetheless. So what's a standing wave? So let me show you a standing wave. A standing wave in a simple, essentially one-dimensional system. Maybe I did this before. I can't remember when last I did this, but okay, I'm doing it anyway. So I've just got a spring here attached at one end, and I can make a wave here where the direction along which the wave extends is left-right, but I'm going to have it wave into the vertical direction. So there, this is a standing wave. It looks like a wave. It's okay, right? The wave, it extends along the horizontal direction, but the cycle is vertical. And actually, I can make the cycle, instead of being purely vertical, I can go around in a loop. Yeah, of course, make life difficult. Oh, of course it got tangled. Don't do that. All right. So what I want to do is I want to make it cycle. I want to make it cycle around us in a circle. So each part of the wave is doing a loop. If you look at the middle, it's not very circular, but that's the idea. It's going around in a cycle. Okay? It's dancing in place by going around in a cycle. And this is one possible standing wave on a spring. And if I go twice as fast, can I do this without breaking something? Now, I'm not going to do it. I'm going to do it non-circular. I'm going to do it vertical. They're very closely related. They have to do with, yeah, they're very closely related. Whether I go in a circle or I go purely vertical, it doesn't matter. But I ought to be able to get, I have to do it at the right frequency and not break something. Well, there I've got another standing wave going. Actually pretty, and I'm going circular now. But that's another standing wave. And you'll notice there are parts that are not moving, what are known as nodes. This has 3 nodes in it. So this is a standing wave with 3 more nodes than the first one. So this is the 4th in a series. The first one had no nodes. The second one, which I didn't get, has 1 node, then 2 nodes, and this is 3 nodes, and that's all I want to do. I think it's enough. Okay? So it is possible to get waves on a, it's a finite system, that is, it has ends. On a finite system, the basic standing waves, the basic waves that can live on that, on a system that has ends, are standing waves, ones that dance in place. I showed you 2 of them, what's known as the fundamental, which is the one that was doing this, or doing that. And in fact, the third overtone, which was the one that had 3 nodes. All right? So that's the standing waves that you get on a one-dimensional system like a spring. On a 2-dimensional system like the head of a drum or the water in a glass of water, then you get 2-dimensional standing waves. They extend. They're finite again. They're limited by the ends of the water, for example, or the end of the drum. But the wave has 2 dimensions over which it's got an interesting extent, and it's waving, which is to say moving, cycling, in the third possible dimension, vertically. Okay? I can't show you a 3-dimensional wave very easily because for a 3-dimensional wave, it's in a box, say, it's limited. It's got 3 dimensions over which it extends, and it's waving, and well, it can't go into another dimension because it's out of dimensions. So it has to wave in some other way. Something else is cycling. And an example of this would be sound in a box. You can get a standing wave of sound in a box where the waving is fluctuations in pressure. And so you can get standing waves, no problem getting standing waves in a box. What I'm thinking of is my freshman year in college when one of my friends down the end of the hall had an 18-inch woofer on his bass electric guitar, and sometimes it would just get essentially feedback. And it would set up standing waves in my hall, and they were really loud in the whole hall, and you could walk, as you walked along, you hear nothing, and then you go a little farther, wow, it's loud, and then nothing, and really loud. It was because it was a standing wave, and it had nodes, and the nodes were fine, and then you step into the middle where it's not a node, wow, okay, and it's a low frequency there that you feel when a car drives by you. It's one of the bass cars go by. Okay, you all right with the idea of a standing waves in a limited system? Well, an electron in an atom is a standing wave too. It's three-dimensional, so it extends around. It's limited essentially by the size of the atom. So it's small. The edges of the atom are fuzzy, so let's not worry about that. But basically, it's a limited system. And where is it waving into quantum mechanically? It's waving into. It has something that's known as a phase, which is it well defined in any way? Not really. It's going through a cycle. And just as I was cycling the string around in a loop, the phase sort of cycles around in a loop. For the electron, it doesn't have a sort of a physical character to it that I can describe. It's just going through this phase, and so you've got the electron standing there, dancing away. And one of the ways I present that, and I'll do this, I'll flip ahead to this, is as color. You can imagine cycling through the colors. And so what I've drawn here, and I'll go back to the previous slides in a second. What I've drawn here is the most simple of the standing waves for an electron in an atom. They're not stretched out from left to right because the electron is negatively charged and the nucleus of the atom is positively charged. The electron really wraps itself around that positive charge. It wants to be snug in there close because that reduces its total potential energy. So it wraps around, come back here, it wraps around the nucleus. Here's the electron, and I'm letting it cycle with time from red to yellow to green to blue to red to yellow to green to blue. It's sitting there dancing in place as a standing wave around the nucleus. It actually has, the wave isn't just at the surface. I picked one surface and let the colors dance, but it all surfaces. It's actually strongest at a certain point, some distance from the nucleus. Is that true? I should be careful. Just as this wave, when it's dancing there, the fundamental dancing there, it's strong right in the middle. It's also present elsewhere along the wave, except at the nodes. This guy is present, it has no nodes. It's present right at the nucleus, in fact, and it goes out, and then it peters out at some distance from the nucleus and dances there. And that's what you may have learned of in chemistry. That's the 1s orbital, which is just a way of labeling that it happens to be the lowest energy orbital. The word orbital is the quantum mechanical, not equivalent, but to an orbit. The electron isn't literally orbiting anymore. It is in an orbital, which is the standing wave that's left when you realize that this is a quantum mechanical system and not a classical one with a little ball going around another little ball. So that is the 1s orbital, the lowest energy standing wave around a nucleus. And the 2s orbital looks a lot alike. The difference between the 2s orbital and the 1s orbital is that it has a node in it. But the node that I was showing you here when I had the string dancing, those nodes were points along the left-right line. The nodes in a two-dimensional standing wave, like on the head of a drum, are often lines, not points, they're lines, because they can extend over a second dimension. And the standing waves in a three-dimensional, the nodes in the three-dimensional standing wave can be surfaces. You're going up in dimensions. And so the surface, there's a surface of node in the 2s orbital there's a specific distance from the nucleus where there is no wave, where the wave is nothing. It's got no amplitude as it's measured. And so it's still dancing in place, but the outside is going one color and the inside is actually going the opposite color. So it's going, on the outside it's going red, yellow, green, blue, yellow, green, blue, according to my little way of illustrating it. And inside it's going green, blue, red, yellow, green, blue, red, yellow. It's on the other direction in the phase. Then there are other standing waves that are not spherical anymore. You've bumped into these guys in chemistry probably, the 2s orbitals, the 3d orbitals. They're all just standing waves around that nucleus. So hopefully you've encountered them in the past by name. They probably didn't mean anything to you because what is this thing? It's a standing wave of electrons. It's one electron in a standing wave around the nucleus, dancing in place. Is that okay? Or questions at least. I mean, it's mysterious, and I can't like make it. Can I make it any simpler? Not without big effort. It's pretty much that's what it is. All right. Some more about quantum physics before I blast past it. Just to put it in perspective, somewhere around the year 1900, physicists / scientists thought they really understood the universe pretty well, except for these couple of nagging problems. One of which, incidentally, was associated with the Blackbody Spectrum. The spectrum of the sun, remember, it gets stronger as you come into the infrared, peaks in the visible, and then it goes back down into lower and lower intensity as you get to the ultraviolet. And there was the physicists of the sort of the late 1800s were suffering over that return back down to low intensity. They understood why the intensity got bigger and bigger as you head towards green, and then it's, towards the mid frequencies of the visible. They couldn't understand why the frequencies then tapered off. Why don't you have a lot of ultraviolet? And it was called the problem was called the ultraviolet catastrophe, because classical physics predicts that there should be just, as you go to higher and higher frequencies, there should be more and more intensity. Why does it stop? The answer is it stops because of quantum physics, but they didn't know it then. So that was, the point is that they thought they knew, well, they thought they knew everything. Everybody always thinks they know everything. But these little teeny problems, it was like the little threads on the sweater. Oh, just a little problem. The whole thing came apart. So they began to discover that there were some pieces, some major pieces missing in the physics of that era. The two that most familiar to you, at least by name, are quantum physics and relativity. And so they both came out sort of at about the same time. Einstein was central to both of them, and the world changed. There's the big revolution in physics. In all likelihood, it will never be duplicated. It was the magic era. And what was observed was that in classical physics, that is to say physics before 1900, people thought that objects came in two completely separate categories, sort of particles, like a billiard ball, and smaller billiard balls, and finally atoms maybe. Those were particles. And then there were things that were light, that were wave-like, like light and sound, and things on water. Pure wave, pure particle, nothing, no crisscross. In reality, everything has a particle-like character and a wave-like character. It's just that sometimes you see more of one than the other. And so while billiard balls, it's hard to see their wave-like character. When you get to the small stuff like electrons, it's not hard to see the wave-like character. It's there. And you see in something like an electron, you see its particle-like character when you go looking for it. Where is it? It's there. That's like what you do with a particle. When you create it or collect it, that's when you see its particle-like. But when you let it just move on its own, don't pay attention to it directly, its wave-like character starts showing up. So the electrons in atoms, they're just there around the nucleus, and while you don't go looking for them, they're there in a wave. And they're not particle-like at all. So that's the world of seemingly particle objects. Turns out they have wave character. And seemingly wave character things also have particle-like character. And it's the same, follows the same rules. That when you create them or collect them, or create or destroy them, things like light, then they're particle-like. So although most of the time we pay attention to light traveling, the act of creating light or the act of absorbing light, that's very particle-like in character. And that notion that light has a particle-like behavior, it comes in pieces, or quanta. That's what, the origin of the name quantum mechanics is because light is created and absorbed in quanta, in pieces. And it turns out that if you look at the simplest of light waves, just one pure frequency, very simple, it has to create that little wave. We'll make it as small as we can. It turns out you can't make it arbitrary size. The smallest you can make it is one quanta. And so you make it one quanta light wave, off it goes. When you collect it, it will deliver, the wave will then vanish. It was a wave, and that goes from, it doesn't just get like to half intensity, it's gone completely, because there was only one quanta worth in there, and you've collected a certain amount of energy. And that one quanta light wave is called a photon. You may have heard of photons before, like photon torpedoes and stuff. Well, this is what a real photon is. It's a single quanta of light. And it turns out there's a relationship between the frequency of the light and the energy in it, in a single quanta. And they're proportional. And the constant proportionality is known as Planck's constant. It's a very tiny amount. The amount of energy carried by one quanta of visible light is really little. We'll get later on to how much it is. I mean, it's not zero. It's so little that it's barely able to do anything interesting like change a molecule's conformation, rearrange a molecule a little bit. And that's how our eyes see the light, is we actually have molecules in our eyes that when they absorb one quantum, one photon of visible light, they undergo a structural change just enough to trigger nerve impulses and so on, and we can see them. We can see the light. And so we're somewhere close to being able to sense individual photons of light in the dark. I'm not sure whether humans can actually do that, but it's somewhere very close. There are machines that can see the photons one at a time. But visible light, where I'm going with this is visible light the photons carry just enough energy to make the subtle changes in very sensitive molecules. If you go to higher frequency light, now I'm going to public service announcement mode. You go to higher frequency light, it carries more energy per photon. And you get into the ultraviolet. And now it carries enough energy per photon to rearrange molecules. And this is why ultraviolet light exposure is potentially hazardous. Because you're absorbing, the photons are coming in, they're actually individually able to do chemical damage to you. And ultimately, though, the big fear is genetic damage that causes cancer. So this is where it comes from. You expose yourself to the high energy. They're along with being high frequency light, it's high energy light. And it has enough energy to cause chemical damage, and that's hazardous. X-rays even more so, gamma rays still more so. These are higher and higher frequency light. Is that okay? Okay, so the point at this point is that electrons, when you let them travel, they travel as waves. And light, when you try to collect it or create it, it behaves as particles. So here are the electrons living in an atom. They tend to have these wave-like characters. And these are the simplest standing waves for a single electron in a single atom. The only atom that's really like that is hydrogen. Once you get into the bigger atoms, there are multiple electrons around. The electrons actually interact with one another because each one's negatively charged. They don't like to be in each other's way. So they're not oversimplified, these standing waves, or so-called orbitals, but they get modified when you get into complex, the bigger atoms. Okay, so my goal is, and what I'll finish with, I've still got enough time to finish the story of neon. When you build a neon atom, the electrons go into these orbitals, and again, they start talking to each other, and so the orbitals get a little bit modified. But where do they end up? Well, neon has plus 10, the nucleus has 10 protons in it, which means that for it to become electrically neutral, it will gather, as we talked about way back early in the semester, it'll gather 10 electrons before it becomes neutral, and then it'll be happy and nothing further is likely to happen. So 10 electrons will come into the neon atom, join it, build the atom, and they'll go into their standing waves. Well, why don't they all go into the lowest standing wave? There's an energy drive to do that. It takes a lot of energy to not be in the lowest standing wave. And so at ordinary temperatures and exposures, there's not a lot of energy around for random stupid decisions. So the electrons would, in fact, all pile into the lowest energy state if they could. That would sort of settle all the squabbles over who gets the extra energy associated with room temperature. So they would all pile in there, but there's another observed rule in nature, and that is that particles of the type that electrons belong to, a class known as Fermi particles. Fermi particles have to follow a rule known as the Pauli exclusion principle. And the Pauli exclusion principle observes that no two indistinguishable Fermi particles ever occupy the same quantum wave. There's physics underlying this that actually I don't remember well at this point. Why the Pauli exclusion? It applies. It's got to do with field theory that it's gotten rusty in me. So the point is, you can't have all the electrons piling up in that one level. It's forbidden by nature, specifically this Pauli exclusion principle. It turns out you can, however, get 2 electrons into a single standing wave. Why? Because electrons have 2 possible internal states, which I've described before in the context of magnetism: spin up and spin down. You can have, by virtue of angular momentum, you can distinguish 2 electrons according to one that has the angular momentum up, for example, and one of them has angular momentum down. Why they can't have angular momentum 0 and stuff like that, that's complicated too. But it turns out they only can have 2 choices, and those make, having spin up versus spin down, that distinguishes 2 electrons. So you can have 2 of them in a quantum standing wave, and that's it. 1 spin up, 1 spin down, and you're full. So therefore, in building a neon atom, you need 5 standing waves. The 5 lowest energy standing waves are occupied by electrons. Occupied is a jargon term saying that there are electrons exhibiting those 5 standing waves. One of them spin up, one of them spin down in each of the standing waves. And that's what's called the ground state of neon, the state that it's normally found in at room temperature. If you expose that neon atom to extra energy in some manner or other, smash things into it, you can move the electrons out of the standing waves that they're supposed to be in the ground state and pop one of them up into an excited state. That is a state in which it's in the wrong standing wave. It's in a standing wave that normally isn't occupied. No electron normally exhibits that standing wave. And once it's up there, it will sit there for a while, but again, at room temperature, it's got too much energy for its environment. It's not sharing equally. It's got energy it doesn't deserve, and it will eventually drop back into one of the lower standing waves. It will return towards the ground state. And in doing so, it has to give up energy. And where does the energy go? Well, it can go out by way of collisions and other things, but it often goes out as light, by what's known as a radiative transition. It goes out as a particle of light, a photon. And the photon carries away the extra energy. And because the energy in a photon is proportional to its frequency, the energy that thing carries away determines its frequency, therefore its color. And what color is preferred for emission by neon? Red. So what you're seeing here, this is a gas discharge. We are taking neon that was sitting there minding its own business for the past half hour, and we're smashing charged particles into it with lots of energy. So there's a high voltage power supply in here. It's throwing charged particles through there, exciting the neon into orbitals that it would not normally be in. They stay there briefly, and then they drop into lower orbitals, that is lower in energy, by emitting visible light. And the visible light is primarily red, although not entirely red, and I'll show you, next time I'll show you the details. It's got other colors there, but that is the red of a neon sign. It's neon going basically from its favorite excited state to its ground state. This is the one that nature loves to make it go, and it emits a red photon of light because the energy gap between those two states is just right to build a red photon. All right, so that's it for Monday. We'll go on to this on Wednesday.